Okay, so here's the final episode with how to train a model using colored images. So we'll start with the imports that we previously did before. So these steps are practically the same as prior, with just a little bit of examples that I also used before to show what type of data we are working with. So here we are turning the image from BGR to RGB using a 64 by 64 dimension, then just creating the test set images. Now the next step that I'll do is, when this finishes, is creating the test images data, putting it to an NumPy array, and basically repeating this prior step that I did for the grayscale images, creating duplicates. That's the flipped image. Then training the model, and then finally just considering this to be finished, including pickling all of this. Now, since this is also similar to what you should be doing if you're working on Kaggle, I'll use the test folder in this case to make predictions whether this is a cat and a dog. Then using that, we'll see how well it performs compared to um, real data, because we'll be able to open the image and see if it's actually predicted it correctly or wrongfully. Then we'll create the pandas file, well, a CSV file using pandas, and this file will now be in the format that they expect the submission to be in. And what you just basically do at this point is just submit the file, and then it's automatically graded, and you will basically be ranked based on that. Now the cool thing is you can actually resubmit as many times as possible, and the only thing they do recommend is you do not do this manually. So don't manually go to the folder and manually label this, because eventually you will find a problem that will be next to infeasible to do this. A good example will be, these are examples where you were to determine from an X-ray whether an image contains cancer or not. So from an X-ray, a doctor can actually see a tumor, and your point would be to be able to detect whether there is a tumor visible on this or not. And there may be multiple classes. Let's say a malignant tumor, so I don't think you can be able to tell it's malignant from just a pure X-ray. But let's say it's not even as simple as two categories, yes or no. There's severity of it all, based on maybe the size or the frequency of detected tumors. So add this all up, and if you wanted to do now continuously do this manually, you would be putting yourself at a corner where you would practically have to learn how to do this. Basically learn how to classify and do this, and more or less likely your results may be, unless you can actually learn how to train. Okay, just a moment. So I'm looking at how many items you have, so it's okay. So that's going to create 50,000 images. So as I was saying, it's hard to imagine that in the time period that you are supposed to do this, you go and do research on how to do X-ray scanning and basically figure out how this works. And of course, in the long run, if someone actually now wants to work with you, they'll ask for the training model, which you'll not be able to provide, which quickly will out you out as someone who's not skilled at this. So the only thing that in this case you need to do is learn how to design a model, learn how to get its classification, learn how to use it to give out an output, because even on Kaggle there are competitions. So these competitions are, the most cool thing about them is they have a price range which is pretty high. Some of them actually go up to $500,000. So it's a pretty neat amount of prize money to win. But if you actually rank at the top figures, so let's say the top number one, two, or three, where probably that's where they give the prize money, your CSV results will not be the only thing that they'll ask for. They'll also ask for your model. So if you are doing this with a nefarious mind of just providing a concocted CSV that you did manually to win the prize money, the next step of being asked to prove you could do this by providing your model, you basically fail that, and more likely you risk even getting your account disabled on the site. So that's just a fair warning that Kaggle is a serious site in terms of consideration of whether you actually are doing this good or not. So other things that people do on the site is, if there is a competition, well, not necessarily a competition, it's a challenge where basically someone is going to provide a data set and a challenge without any monetary gain. So people do tend to do same case as you have this Jupyter notebook, guide someone only to the point of understanding how to process the data. So the rules of the site is you can't give someone your whole recipe. Some people do, and in one way or another you can get it even on other sources like GitHub. But the more point is that so that to avoid people actually copy pasting each other's codes, which tended to happen a lot here, at a certain point, there's a discussion that we actually went on that some data scientists felt that the site practically became a place where everyone was doing the same thing and there was no innovation, where eventually they went around it and recommended that people who are uploading the code preferably not show you every single step, just the necessary things. For example, if you're looking at X-ray data, how to process the image in whatever format that it's coming in. Also the same case for novice type of data you've never seen before. Let's say audio files. You are supposed to maybe create something that can talk like a human or emulate a human's voice. So that's a voice emulator. Or let's say if you are trying to make something that can generate fake images, that's GAN, general adversarial networks, and all sorts of things similar to this. So if you are in that situation where you're working with data you've never seen before, and you're grappling how to process the data, how to analyze it, maybe even how to feed it to your model, this is going to get you from 0 to 100 real quick. So you'll see how other people are doing it, you'll review with other people, you can discuss with them, because practically in coding, you should never consider yourself as a self-contained expert at something. That's the reason you have sites like Stack Overflow where people ask questions, sites like GitHub where people share code, and basically the community, in a good sense, support each other and share their ideas. That's the core logic of the open source community, where people share not only their projects and codes, like you can see tools like TensorFlow or Keras. They're not proprietary, so you don't pay for them. They're free to use even on a commercial basis. You could use it to design a model that would classify anything, and you wouldn't be required to pay the body that designed this code, even after they continuously do updates. Even after you report bugs and they fix them, you are under no obligation to do this. Only out of the kindness of your heart, and more so if you're in a position to. This tends to come more from companies that interact with this software on a regular basis, and they actually want the software to not only be up to date, but they want to support it, and more so to the point that assisting a community has led to even there being a core list of developers who work on this 24/7 based on the contributions of these tools. So this is more common for very popular libraries. If the library is not created by a company like Google, for example, which would be the case of TensorFlow, even though it has an open source community that also contributes to it, it also has its internal group that contributes to it. Though the caveat to this is it's a known fact that the TensorFlow that we are using right now, Google has its own internal one, which is different. So probably more ways than one, more advanced and more tailored for their system because they have a different architecture. So it may also be tailor-made to distribute the tasks over the large supercomputers and distributed networks that they have, so that training a model on their end is remarkably fast compared even if you had your own pretty fast PC or a number of PCs connected. There's a chip that they developed, it's called a TPU, which is a TensorFlow processing unit, and it's marked to be the most fastest and efficient CPU, well GPU. It's a GPU processing unit for doing the type of calculations you tend to do with machine learning. So the last I checked, the chip isn't being sold to people. They're not selling it. They are leasing the server that hosts it. They may have changed their mind. So if you are in a position to consider having your own machine learning platform, if they start selling it, it's a consideration. If you're designing a machine practically for only one purpose, you should check out and see whether they've changed their outlook to decide to start selling it. And if they have same case as the way you would have bought an NVIDIA chip. So okay, so it still looks, why can I buy TPU to learn? So it doesn't look like they're actually selling it. So okay, practically if you are designing this, on my PC I have an AMD GPU which isn't compatible with CUDA, which is what's being used to control the graphics card to do the parallel processing needed for this. So I'm using TensorFlow only on my PC CPU. So that's a lot slower than using a GPU. So if you have a GPU, it's considerably faster. But if you have, so basically in this case, I'd recommend buying an NVIDIA, though more modern AMDs may be able to support CUDA, but so I'd recommend you do a research if you're buying a machine for this. So it seems they are not interested in selling it because I believe the reason is it's proprietary technology and they don't want uh, duplicates to be on the market. So you can use it from their platform, which is the Google Cloud, and basically run your code on a TPU server, which in all intents and purposes, if you know how machine learning works, the process of training is the slowest process possible. So that may take from hours to days, depending on not only your PC, but the amount of data and the complexity of your data and the complexity of your model. So you're looking at hours to days. In my case, it takes hours to complete. And so whether it takes hours or days to complete, if you follow these important steps of using an early stopping and a checkpoint to get you not only your best model, but prevent from continuously trading when there is no visible amount of change. So in this case also Just to quickly review the model, you're looking at a patience of 8. The batch size is 64. The epochs are 100. The layer is 40 with a 3x3 window. The input side is different right now because it's 64 by 64. Then 3 to denote the colors, which is RGB. So this is an image that is 3 layers deep. And then it goes to an ReLU, then a max pooling of 2x2. So this is how I was saying you could actually have dropouts in multiple places. So you have 1, 2, 3 dropouts in between. So I did try this once before, and I found that adding dropouts in between here was not increasing the accuracy. But if you were to look out if you do a research on how models look, deep learning models, the one that I'm working on is practically pretty shallow, so it's a small one, and more so the ones that people do use, like if you were to look at the ones that are used in competitions, they tend to have somewhere between 50 to 100 layers. In my case here, I'm looking at only 3. So my case of what I'm training on is also simple, just cat versus dog classification, but still working with this and only 3 layers. So working with this with 3 layers is okay, but maybe if I work with a full model, instead of getting 77%, I maybe would have got it to 80 or 90%. So that's a caveat to consider. Okay, so I think that's everything for this. So I want to just show you an example of a deep neural network. So I can't actually remember right now the names of the last. There's a list of ones that actually went on to perform well enough in image classification. Yes, okay. So here you have the VGG network. So VGG network. So here it's receiving an image dimension that's 224 pixels by 224, considerably larger than what we had before. And then the first layer is 64 cells deep. It goes through a max pooling times 2, so that decreases the size to not only 112 and 112, it also increases the dimension, the depth to 128. It does another max pooling and another max pooling, and this point now decreases the level of the dimensions of this to a smaller one, from 28 by 28 to 14 by 14. So here we can see how they've labeled the layers by the color. So the black ones are convolution plus ReLU, similar to what you have here, convolution and a ReLU. And the next step is max pooling, which you also have here 2 by 2, which now basically decreases the dimensions but decreases the depth. Then doing this again decreases the dimension and increases the depth. The depth again decreasing the dimension, then increasing the depth. But in this case, the depth doesn't increase also. So I'm not sure if it's a typo or intentionally they avoided using a max pooling. But still, so this layer and this next one decreases the dimensions to finally 7 by 7. Then using a fully connected, which is a flattened here, they get back their 1 by 1 by 496 by 1 by 1. Then the final 100 here equals to a softmax, then does a prediction. So here you're looking at almost about 4 layers, but in terms of the complexity, this one is larger than what I had prior, primarily because the image input is larger. But also, since this came out, there have been multiple others which are much bigger and are much more complex. So this code actually here is pretty interesting because it shows you how to use a pre-existing model. Since you can download Keras comes with predefined models which you can provide data inside and just basically train it. So this would be an angle of trying this, and in this case he seems to have gone with a dimension input of 150 by 50. So I could have also done the same and gone with my 64 by 64 and basically train the model and see how it performs. So there is a lot and plenty around to go around on how to tackle the same problem of getting your model to the best performance possible. Since Keras has its own pre-trained model or predefined model to be exact, you can just basically use that, feed in data, and get back the result. Or you define your own model. So with these two angles, you have two ways to tackle the same problem. So it's basically up to you to decide which one is the best one for you. So with that in mind, I'll wait for this one to finish. Then we'll see how it performs and finally finish by creating the output pandas file so that you can submit it to Kaggle if you now actually want to see how well your data performs based on validation. Okay, so the colored model finished training, and this actually went faster than usual by finishing at only the 10th epoch. Now if you look here at the results from the tensor board, you can see that its graph basically has the poorest results with final accuracy of 51% and a loss that barely changed over time. So this model had a poor way of learning, so it wasn't basically learning well enough compared to the other models. So one of the things that could be the results for this is this last dense layer was too small. Another one may be the sizes of these convolution 2D models were also rather small. So there are two angles for this. One would be working with the grayscale model here. because I already saved it before, I can preload it again and use it to I can use it to retrain the model, well, to get the results for the test set. So with that approach, I wouldn't have to retrain this model by redesigning it, and this will just be a completion of this. Whereas if I retrain the model, I'd have to wait to see how it performs, and maybe even cancel it in between if it's actually performing poorly, and readjust the settings again. So maybe I can give you some pointers of what I would have done to change this. Increase the last dense layer, because here we're looking at 10, and here we had a dense layer of 50. So that's a large drop of the last dense layer. And this is the one that actually spreads out possibilities to this last dense layer of 1 here. So 10 is rather small, and 50 would have been a much better result, and a much better layer possibly. Another one would be just be having the layers be more synchronous with this. So that would be another technique to make this work. So with that in mind, I think what I'm going to do is, using the colored model, I'm going to redesign this, let it run, just to see if these new changes will be good enough. But I'm also going to reload this model. So this training model that you're using, we've already saved before, which now has the highest results, which is this one right here. I'm going to use this one to create the required sample submission CSV, which is this. So with that, you'll learn how to reuse a pre-saved model, get back your test image data, and use that to actually get back your prediction, and then get back your prediction set with that, create your submission file. So you'll know how to reuse an old model and basically get the data. And also at the same time, I'm going to redesign this so that you can see the best of two sides of not only how to preload another model, but also how to rework a model that has results that actually proves to be worse than what you'd expected.